Okay, so this is the outline of the talk. First, I'll talk about kind of industry trends and the reason for why we are embarking on this research. Then I'll give some data from some early experiences with the Tegra CPUs. And then I'll talk about the future and our prototype roadmap that we have at the BSc. So if you look at the HPC market, there's this top 500 list, which lists the 500 largest machines around the world in supercomputing. And this list started in '93. And what I'm showing here is the number of systems in this list, the top 500, from various classes. So you could see in '93 or in the early '90s to the mid-'90s, HPC was dominated by vector and SIMD machines from companies like Convex and Cray and so on. But over the course of the '90s, microprocessors basically took over this space. So to begin with, things like the DEC Alpha and the Spark and the MIPS machines took over HPC and displaced companies like Cray and so on. And then around 2000, there was a switch from these earlier RISC microprocessors to x86. Quite a dramatic change over a small number of years. And the reason for this was not that microprocessors were somehow higher performance than these older machines. Definitely not. They were a lot lower in performance. But they were so much cheaper and also more energy efficient, but mainly cheaper, that that basically drove the change. And this required also a change in programming model as you went from distributed memory computing to distributed memory and MPI programming models and so on. But the advantage was large enough to make up for this. So if you look, I put this line there at about '94 when the crossover kind of happened. And if you look at the timing of the transition, here I'm plotting, now the line is the same place, even though the scales moved a bit in '94 or so. And I plotted double precision, million flops per second. And the red line is the older kind of Cray machines, vector and SIMD, and coming up quite rapidly are the microprocessors. And you could see at that sort of point on this log scale, maybe a factor of 10 or so in performance was the difference. And the advantage, as I said before, was the commodity volume economics. So now, in 2013, where is the commodity market? And it's quite clear that it's the mobile market. The enormous growth, an enormous number of smartphones and tablets. Some numbers there that mean this market is much, much larger than the laptops and desktops and server space. And at the top, we've got this tiny niche, which is us, which is the HPC market. So this started to make us think about, well, maybe the same thing could happen from the mobile space. So at the top is the graph that I showed before. And at the bottom, we've got a very similar sort of looking graph. This doesn't prove a thing, but it kind of implies maybe something, maybe now is the time that it may kind of gather space. And one thing I just put this in as a last minute addition to the slides is to talk a little bit about power and energy consumption. So even in supercomputing, if you're not familiar with this market, power consumption is absolutely critical. And in fact, you can say that power consumption is important across the whole computing space, whether it's ambient energy that's your limiting factor, or whether it's the batteries or the thermal constraints maybe in the middle. To put some numbers on this, the top machines at the moment, top supercomputing machines, are around 10 megawatts. And the next target that everybody in the HPC space is talking about is the exaflop. So a 10 to the 18 floating point operations per second. by 2020 or something. Maybe it'll slip a bit, but this is what they're talking about. And using today's technology, that would be 1/2 a gigawatt for a single supercomputer. So you're seriously saying that you have to build a dedicated nuclear power plant next door to your supercomputer. And that does not seem sensible. And it's, so this basically coming down back to today, there's the power constraints in terms of negotiating a power supply that can give you 10 megawatts, plus of course the operational expenses in terms of paying for this. So power consumption is important. But having said that, this is not our motivation for looking at mobile SoCs, because there is a gap. Historically, there's a gap between the mobile space, mostly dominated by ARM, and x86 parts, and where historically the ARM parts have much better power consumption. But we believe that the major players in the x86 space will increase their energy efficiency over time to narrow this gap. And even if this gap persists, it wouldn't be enough, we see, to encourage people to change their ISA. So the motivation that we really push is the economical one, not the power consumption. The power consumption has to stay state of the art, but no more than that. So that's basically the outline of the motivation. Then I'll talk a little bit about our experience. So we have the Mont-Blanc project, which started in October 2011. It's a European-funded project for 3 years. And the objective is to develop a European, so we can push the European angle, of course, exascale approach based on embedded power-efficient technology. And we have 3 objectives. So the first is to build a prototype machine, which I'll talk about later, and then to design the next generation for what we would do next, and to work on porting the system software and the applications to mobile SoC, basically to ARM ISA. And these are the partners. It's coordinated or led by the BSC. The machines are being integrated by the French company Bull. ARM is a partner, and some application partners and Nodal on the interconnect side. So I have just a few kind of numbers here. It's not really the focus of this talk. The question is, are mobile SoCs ready for HPC now? Are they already ready? So this is the work using Tegra 2, Tegra 3, and sort of unfortunately for this work, we've actually used microkernels rather than full applications. We have full applications in the Mont-Blanc project, and we're beginning to benchmark them and get proper numbers. But here we just have some microkernels, and we use these because it's very easy to port a few hundred lines to a different architecture than a full application. So we used these 2 platforms, Tegra 2 developer board, and the Karma kit, which has been renamed to Kayla. Well, I won't say why. So this Tegra 2 board, this is Tegra 3, and the third option is the Karma kit with the mobile GPU, so a laptop GPU on it. And then these are the benchmarks. Maybe not so interesting, but just kind of a wide range of properties. And here we have speed up normalized to Tegra 2. We see a small difference from Tegra 2 to Tegra 3, and a fairly large one. Most of these run well on the GPU. In terms of energy, we've also got a slight problem. I was very interested to see the demonstration from the Samsung people in terms of measuring the power consumption of the different power domains in the SoC, because with this we found it difficult to measure where the power is actually going in the board. And these boards, we get the impression, haven't been designed to themselves have low power consumption. So we find a lot of power going on things that are not the SoC or the memory. And at the moment, these numbers, there is an improvement in power consumption from Tegra 2 to Tegra 3 and to the Quadro, but it's not as large, and we really need to improve the way that we measure the energy here. And we have more results on multi-core. The Tegra 2, of course, is dual-core. Tegra 3 has 4 cores, so if you take that into account, you get basically the overheads that are on the board become less of a problem when you have more cores, because you're getting more computation done. And then this maybe is the most interesting thing, because it's showing over time the gap. There's still a large gap between the Tegra 2 and the Tegra 3 and so on, and the Sandy Bridge. But the gap is decreasing. We're starting to get some results on the Exynos 5, the Samsung Exynos 5, using it with the Armdale board, and we have a factor of almost 5 difference in performance, I believe ignoring the GPU in both cases. And from what we've heard about ARM v8 performance, we see that coming to a factor of 2 or so. So there's a difference in performance, but maybe with twice as many nodes, you start to close the gap. And if we go back to the motivation I gave at the beginning, we don't have to reach the same performance for the economical argument to carry us into the space. We just have to be close enough that the gap isn't enormous. So this basically summarizes what I said, that the benchmarks are showing that the energy to solution is reducing, and more critically, the gap in performance is closing, and that future mobile SoCs will be increasingly competitive. Although there are some missing features that maybe will come up in the questions regarding the mobile SoCs. So then, this is our prototype roadmap. So in 2011, we constructed this Tibidabo machine, which I'll talk about more in the next slide. And this year, well, it's actually, okay, they must go like that. We're putting together Pedraforca, which is Tegra 3 plus discrete GPU, and then the Mont-Blanc prototype itself, which I'll also talk about, is expected later this year. So this one's financed by Mont-Blanc. These are financed by Price, which is an important supercomputing infrastructure project. And so we have this sequence of prototypes because the prototypes are crucial for the software development. So, and each time we build one, we learn a number of interesting things that we didn't expect to be a problem that we can use to improve the next one. So this is a Tibidabo cluster. We have a small Tegra 2 compute card, which goes on this carrier board, and then we put 8 of them in a kind of rackable blade together with a bare power supply, which probably wouldn't be allowed in this country, but in Spain we have a bare power supply, and then we put them in these 2 racks here. And for a while we ran this in our coffee room, and we have users from around the world logging in, and the software stack is basically similar to what they expect to see. So it is possible to deploy a cluster using smartphone processors. I guess I can go through some of the numbers here. We have 256 nodes in total. Dual core, so 512 cores. And then Pedraforca is in 2 parts. The first part is a small cluster of the Karma kits with 1 gigabit interconnect. And stage 2 is built by Bull. We're using NVIDIA Kepler GPU together with Tegra 3. And then the Mont-Blanc prototype, we chose the Samsung Exynos 5 dual core. We considered many other chips. The Tegra 4 we couldn't use because there was no PCI Express on it, and we were constrained by the availability of different cores, and we settled on this Samsung part, which is dual core Cortex A15 plus a Mali T604 GPU. So it's integrated GPU with shared memory and so on, no power wasted on the PCI Express. And then we put 15 of these cards in this rack thing here, standing up. And then this is basically each one of these 9 things with the green dot in the middle, with slides into this chassis here. This is a kind of switch and monitoring thing up there. And then we put this in we will put this in a bull enclosure and deploy this later this year. So this is actually the end of my talk now. So next steps, we're not there yet with our killer mobile processors, but we see this as a very important area of research, and we see that sooner or later we could see it really happen, and we will see a supercomputer because we're building it, and we have architecture defined, and then you can follow the project from the project website and Facebook and so on. So that's the end of my talk. So any questions?